invited. We're really honored to have here Aswin. So Aswin is associate professor in the Department of Computer Science at Duke. And he is also co-founder of Tumult Labs. He was previously a research scientist in the knowledge management group at Yahoo Research. Well, Ashwin has won numerous awards. I think too many for me to list them all, but one particular mention of the IEEE Influential Paper Award for the invention of L diversity in 2006. And Ashwin has also collaborated, as John was mentioning, with US Census Bureau, and he is credited with the development of the first real-world application of differential privacy. So we're really excited for your talk. Without further ado, I'll give you the floor.
Oh, thank you very much, Ferdinando. Thank you for inviting me here. It's a great pleasure to give a talk. Let me first try to share my screen. Okay, so can you see my screen? If I can, yep. All right. Okay, so today I wanted to give a slightly less technical talk and more towards what does it mean to deploy differential privacy. This is something that I've been doing for over a decade now, and doing it more actively now that more recently we've started this startup called Tumult Labs, along with two other professors, Jerome McLeod and Michael Hay. And today we want to sort of give you a sense for what does deploying differential privacy in like an organization really mean? What does the process look like? And is it sort of similar or different from what we think about differential privacy when we write papers and think about research and advise our students? Yeah, so I think that's the main sort of point of this talk. All right, so I mean, this is a mixed audience. I thought I'll just sort of go over what the motivation for differential privacy is. And in a lot of cases, the motivation is that organizations have a lot of sensitive data, and these are very valuable, and they want to share aggregate statistics or machine learning models from the sensitive individual data out to the public. Either hospitals want to release it for researchers, government agencies like the census want to release it to policymakers, social media companies want to sort of study impact of misinformation on elections, so lots of different use cases, right? And these are all really great use cases, and if you're able to enable them, that's more power to us, right? But then, of course, we know that there have been a whole line of attacks that are increasing in volume and sophistication, even if you're releasing only aggregate statistics or you're releasing machine learning models, right? And you've seen some of these, like one of the reasons I got into privacy was in 2006, there was this AOL release search logs, and there was a big privacy breach, right? And there's been a stream of those things which show that you cannot just anonymize data. You can't just remove identifiers. There's always something that will allow you to learn an individual, right? But it's much beyond that. Like even if you're releasing machine learning models, right, you can learn sensitive properties from these machine learning models. And this started with this fundamental work by Reza Shokri and others in 2017, where they showed that even if this machine learning model, you only had black box access to the machine learning model, which is trained on some sensitive data set, then you could use this black box access to learn whether a specific individual was in the training data set or not, right? This is called the membership inference attack. And there have been many more such sort of attacks, and all the way till like now, there's a lot of both empirical and theoretical work that show that these large language models and large machine learning models actually remember parts of the input, some of which might be sensitive, right? And of course, you also heard about sort of reconstruction attack on statistical releases. The US Census Bureau showed this. They actually attacked themselves. They took the 2010 releases that they had from the 2010 decennial census, which actually passed muster. They actually passed through a review process, and they were deemed private. But you were able to use simple reconstruction attacks to reconstruct more than 50% of the US population accurately down to the block, the gender, the race, and so on, right? And this is not just the US Census Bureau. Like there have been we've been sort of stuck in this unending cycle of people trying to invent anonymization algorithms or algorithms or release statistics that don't satisfy differential privacy. And one example was Aircloak, which created their own algorithm. They said attack us, and a couple of people who researchers in differential privacy attacked them using the reconstruction attack. And so they went back and changed their algorithm and made it better supposedly. For the second round, again, they got broken by the same reconstruction attack by a couple of other differential privacy researchers. And so to really you want to break out of this cycle, and one of the big challenges when you're, especially when you're releasing many statistics or language or differential or machine learning models that have lots of parameters, is that maybe releasing a small subset of these is safe enough, right? Using sort of standard notions of statistical disclosure limitation. When you're releasing thousands and millions of parameters or thousands of millions of statistics, right, you sort of start getting a death by a thousand cuts, right? They start combining in some very interesting ways, and you can reveal the underlying database, and that's sort of the fundamental law of information reconstruction. So therefore, organizations are turning to differential privacy. You heard from John about, a lot of other companies are turning as well. So in today's talk, I'm going to talk a little bit about how do you deploy differential privacy, right? So I'll give you sort of a case study of how we, as part of our work at Terminate Labs, help the US government agency share data with differential privacy. And the two sort of high-level takeaways is that the real problem of differential privacy is pretty different from the idealized problem that is studied in the research literature. And it's not just sort of, I mean, usually when you take like a problem in the academia and move to the industry, the problems are different because there's a lot of sort of engineering related challenges and technical challenges that we may not consider in research. But in this case, it's not just that. Like getting deployments right requires solving problems that are often research worthy, and they're not often studied in the academic research because we don't do enough of this. And so if there is time, I'll try to highlight a couple of sort of new technical challenges that I think are interesting, and then I'll conclude. Okay, so this is the outline of the talk. Please feel free to sort of stop me if you want in between the talk, and then yeah, we'll go from there. All right, so I'll give a brief recap of what differential privacy is. I know you guys have seen differential privacy before, but I think it's worth doing this. I'll talk about our experience deploying differential privacy and a little bit about the technical challenges. Okay. So what is differential privacy? So differential privacy, I mean, one of the big things when you go and talk to people in the real world is that they think differential privacy is an algorithm. They think, oh, let's use differential privacy to solve a problem. Differential privacy is not an algorithm, right? It's just a rigorous privacy standard that's expressed in math. Algorithms can satisfy differential privacy. And this is like a big sort of disconnect that a lot of people don't understand. The people who are not sort of familiar with differential don't understand. And this, when you're communicating about differential privacy, is the first point you want to talk to them about. The differential privacy is a rigorous standard, and algorithms can satisfy the privacy standard. And to meet the standard of differential privacy, you want to sort of, your analysis algorithms have to be modified. For example, by adding noise, you could be doing other things as well, right? And for most analysis algorithms, differential privacy variants are known. And these differentiated algorithms allow you to meet your privacy laws in precise and quantifiable ways, right? And another sort of important point is like, you need to acknowledge the fact that differential privacy is just one piece of the puzzle in a lot of situations. You may need other pieces of the puzzle to solve the problem as well. And in particular, differential privacy is sort of orthogonal to crypto frameworks like secure multi-party computation, homomorphic encryption, and so on. So one way I like to think about it is like the differential privacy. When you thinking about like a privacy preserving process, differential privacy is ensuring the privacy of the output, making sure that the output doesn't leak leak a lot about the inputs. Whereas secure computation, fully homomorphic encryption, those are sort of ensuring the privacy of the computation itself, right? Ensuring that the computation itself doesn't leak stuff about the input. And things like zero knowledge proofs and snarks ensure the integrity of the computation if they run on some untrusted or malicious servers. So you guys must have seen this already. What is differential privacy? So the informal privacy guarantee is the following: that if you have a person who's basically allowing their data to be analyzed by some algorithm as part of a larger database, right? What differential privacy ensures is that what an adversary may learn about an individual, say Bob, in the real world, where their data, along with all of the other data in the database, is being analyzed with the algorithm, is roughly the same as what can be learned about Bob if Bob decides to opt out of that computation. So you take Bob's record, you remove Bob's record, or you replace it with random values. So in these two worlds, the probability of generating some output, or the distribution of outputs that are generated with algorithm, should be roughly the same. And that's basically the informal privacy guarantee that differential privacy is, right? And more precisely, what you're looking at is these distributions of outputs, and you want to say that these distributions of outputs are close or similar in some very precise manner, right? Another important point is that differential privacy is not a single definition. It's like you should think of it as a framework. And there are sort of many variants of differential privacy that have been studied and are known, and they all sort of change the underlying definition in different ways. So, for example, the standard notion of differential privacy is what you might have heard is the pure DP, pure differential privacy, where you're looking at the two distributions of outputs that are generated from these sort of neighboring databases, and you want to ensure that the maximum ratio of these probabilities is bounded. Right? So you look at any one output possibility, and you want to say that the probability of that output under the the real world versus the opt-out world, that ratio is bounded by e to the epsilon, right? But then you can also sort of have variants of this. You can have approximate differential privacy where you ensure this bound, but with some small failure probability of delta. There is Renyi and zero concentrated differential privacy, where you're looking at moments of this distribution and then looking at the divergences and bounding those divergences, right? And in all these cases, like all of these make sense in different settings. In particular, these are approximate and Renyi differential privacies are useful when you think about epsilon, not as like an absolute value, but like a random variable. Like you think of privacy as a random variable. So they give you sort of more advanced compositional results. But you can also change how you set up this definition in terms of what your privacy object is. Like whose privacy are you guaranteeing, right? So for example, you could have a data set where each row is an individual, where the standard notion of privacy makes sense. You could have a data set where each person may generate many rows, like a single patient may have many visits, right? And so you can change how neighboring databases are set up, and then you have different sort of definitions there. You can also change what kinds of attacks you want to guard against. So there's this recent paper on capacity-bounded differential privacy that changes the attacks an adversary can launch, and then ensures privacy with respect to that. Right. So again, differential privacy is sort of like a framework which you can instantiate depending on the kind of problem that you're interested in solving. A few sort of important takeaways about differential privacy itself before I move on to the deployment part. First of all, you have this one or set of parameters that allow you to sort of meter privacy. And the main thing is that you can sort of have very sort of quantifiable notions of what privacy means here, right? In pure DP, it's epsilon, right? Higher epsilon, you have potentially more privacy loss, but greater data utility, and vice versa when you have lower epsilon. And so this sort of allows you to sort of quantifiably state a social choice problem where you're trading off between privacy protection epsilon for overall accuracy, right? And this sort of trade-off is going to be sort of very important as we go further in this talk. Another important property is the fact that as you do multiple releases, you can add up, and I'm going to say add up in quotes, algebraically, you can add up what the overall privacy loss is as you release multiple releases. What this does, especially in practice, is like it forces people to rethink how you do privacy in the first place. It forces you to rethink privacy budget or access to data as a finite resource. And this is not something that is sort of unique to privacy. It's also the same in sort of statistics and machine learning, where you don't want to access a data set an infinite number of times because of worries of false discovery or p-hacking and so on, right? And so this is an important property that you need to communicate to someone who is thinking about differential privacy, because this is something that they've never seen before, that you have thinking about access to data as a finite resource. And the final consequence of differential privacy is that differential privacy works usually by adding noise and doing a few other things. And while the amount of noise is proportional to the differential privacy parameter, different algorithms have different ways of adding noise. So the same privacy level, you could have different algorithms that sort of give you drastically different outputs. They all satisfy the same privacy guarantee, but what they end up doing is they preserve properties about different aspects of the data, right? And I'm not going to go too deep into this part, but what this gives rise to is yet another social choice problem. And this is something that Pascal and John sort of alluded to, is that for the same level of privacy, now you have to sort of decide where do you want to focus your privacy budget, or the accuracy that you want to get from the data set. Because of the fundamental law of information reconstruction, you can't preserve everything in the data set. You have to pick and choose what you want to preserve, right? And so therefore, for the same level of accuracy, you may have two algorithms, one that has sort of maybe less overall accuracy, but maybe more equality in the way the algorithm's noise, the noise is added to the data set. Whereas you could have other cases where you have greater overall accuracy, but more inequality in the noise. And there are several papers that talk about this. One of them was a paper from our group in FatStar 2020 that looked at differential privacy and how it impacts downstream analytics and the biases it may introduce. And this was also one of the problems with one of the early releases of the census, where they worried that certain small populations and small towns disappeared, and it was good feedback for the census because they went back and sort of changed their algorithms to make sure that you don't introduce these kinds of bias. But even from an algorithm perspective, there are many algorithms, and you want to sort of be careful which ones you choose, right? And different algorithms may make sense in different places. So I want to introduce this sort of concept, and then I'll come back to this later in the talk. Like as a grad student, for me, the differential privacy problem was sort of something like this, which was, you're given a data set, you're given some privacy model and parameters, and you're given a task. Example, you're given a set or a sequence of queries that you want to answer, right? And you're given an error metric, which is L2 error or L1 error, or I want to ensure that at least these many queries are answered with some accuracy guarantee. And the goal is to design a differential privacy algorithm that satisfies this privacy requirement and generates the output with the least error, right? And this is most of what not differential privacy algorithm design looks like. And this is unfortunately not the same when you go to the real world, and I'll come back to the similar picture in the real world later in the talk. Okay, so just sort of recap differential privacy. I think we all know this, but I think it's good to sort of take away is that it's a rigorous privacy standard, not an algorithm. And outputs generated from differential privacy are sort of future-proof from attacks that haven't been invented. It's nice because it meters privacy laws across different releases. And sort of differential privacy algorithms are known for almost every type of data release. And so with that, let's sort of talk a little bit about what does it mean to deploy differential privacy. And this is sort of work that I've done as part of a startup, Tumult Labs, that was co-founded by me, Jerome McLeod, and Michael Hay. And so the problem we were trying to solve here is basically to support a website that was trying to release data for college students. Okay, so this is actually a real website. You can go check it out. And it allows you to sort of look at what are the what are the outcomes of students who graduated in certain colleges across the US in terms of their income statistics. So you can go in, you can search for example, Massachusetts. It shows you all the Massachusetts universities. And it also shows you certain sort of educational outcomes like graduation rate and so on. But also it shows you sort of things like the salary, like what is the median salary of someone who graduated from Harvard in a certain year. And it gives you a range of different values because depending on what program you graduate from, you have a different median income. Right? So unfortunately, no single agency actually had this data. Right? The Department of Schools, I'm going to call it Department of Schools. So the Department of Schools had access to all the educational records, the educational outcomes of students, the degree programs they completed, their sort of average living costs, and so on. But they didn't have access to the salary data, right? Because I mean, once students graduate from schools, the Department of Schools doesn't track them anymore. That data is with what I'm going to call the Department of Revenue. The Department of Revenue is bound by law to protect all the information provided on tax returns. So in particular, they should not even reveal whether a certain individual filed a tax return. It's called fact of filing. And so their disclosure review board should decide if someone like the Department of School comes and says, hey, can you give us like the salary information of students? What can we release? And if we release something, what is its privacy impact? And how should we transform the data to protect privacy? A lot of the questions that we ask as privacy researchers, but they have to do that just as humans and sort of figure out what they're comfortable with and what they're not comfortable with. Okay, so this was sort of the setup. So this is not a new problem. They've been doing this for a few years now. And the past few years, the data protection was based on suppression and ad hoc distortion of income statistics. And they had some sort of rules of thumb saying if the population group is small enough, then we will not release any salary data, or we will not release any medium salary data, and so on, right? But then over the years, the Department of Schools has been wanting more and more fine-grained information. We want information not only at the school level, but also at the program level. We also want information about whether broken down by their gender. We don't want just the median. We want like the 25th percentile, the 50th percentile. And then, so as the data request increases, now you're breaking down the data set into smaller and smaller groups, and you're releasing more and more statistics about them. And so based on their sort of the Department of Revenue's sort of rules of thumb, right, the suppression led to basically throwing away most of the data. Right, more than 90% of the output was unpublished. And it was also impossible to formally verify privacy because the analysts were now also asking for like multiple data sets, which may be overlapping with each other. And then the individuals appeared more than once in a sensitive data set, and releases are made every year. And this is like an obvious use case for compositional definitions like differential privacy, right? And so in 2020, they decided they have to do differential privacy because they're not able to do anything with their existing techniques. Okay. So this is what we think a differential privacy deployment life cycle looks like. It has 4 stages: configuration, request, negotiation, and release. And I'll go a little bit into each of those. So configuration is the data owner sort of defines the data schema, the type of the data that is there, and also what does privacy mean? Like who is the privacy, what is the privacy object, or what does each individual contribute to, right? Then a data analyst says, hey, this data is there, it looks cool. Let me request some statistics, or let me request some task on it, right? Release a bunch of statistics so that they can support their analysis. But now, I think one point that we usually don't see is the fact that there's a negotiation between the data owner and the data analyst. The data owner has some estimate of how much privacy they want to have in this process. The data analyst usually overestimates the amount of data they want, right? And they have to find some common ground because it's possible that the privacy expectation, under the privacy expectation of the data owner, the accuracy expectation of the data analyst is not going to be satisfied, right? And so there is some negotiation between the 2 parties. And then they sort of decide on, okay, here's the answer, let's sort of go and release. And then the data owner releases then the data to the data analyst. Okay. So in particular, the specifics, like the kinds of queries that they cared about was they had a data set of the form, the ID of a student, the college they went to, their gender, whether they got a grant or not, and their income. So this is the data set that was there on the Department of Revenue side, the data owner side. And the analysts wanted sort of group by aggregation queries, like for each college, give me the count, the first quartile, the second quartile, the third quartile. For every college, also for males, give me the count, the first quartile, second quartile, third quartile, and so on. So they wanted all of this sort of overlapping sort of marginal statistics, not just counts, but sort of quantiles as well. And overall, this sort of ended up being like 10.2 million statistics in all. So people talk about deep learning as having the most number of parameters you estimate. This is like that. You're estimating 10.2 million parameters from a data set in a differential private manner. Right? And so we've developed a privacy platform called Safe Tables, and we use Safe Tables to sort of look at this sort of request and an epsilon and generate a release. I'll just say one slide about safe tables. It's a Python sort of software development kit that implements differential privacy operators. It supports standard aggregation and transformation operations on structured data. So you can do filters, group bys, joins, maps, and then you can do like counts and quantize and so on. It's a secure and hardened implementation, and it's inspired by the design of Ectelo and the OpenDP privacy framework. So therefore, it has a compositional design to allow for multiple privacy definitions. And it also is flexible, so it can sort of support multiple algorithmic strategies and optimization. So I won't talk too much about the sort of technical specs of SDK, but I'll sort of tell you what exactly happened when we sort of implemented a solution for them. So the important feature that was required was this kind of accuracy profiling. So the data owner's disclosure review board needed some estimate of, if I use some epsilon, right, what is the accuracy I'm going to see, right? And in particular, they sort of wanted it to see in this sort of form where for different sort of cell sizes, right? So remember, you have 10.2 million statistics. Each statistic is like for a small group of people, right? Sometimes that group is small, like may only have 5 people. Sometimes that group is large, it may have 1,000 people in it, right? So depending on the size of that cell, what does the error look like? So clearly, if your cell size is small, your error is going to be high, right? At least relative error is going to be high. Or if you're looking at things like medians, the median error is going to be high for small cells, and your median error is going to be small for large cells, right? And so this sort of accuracy profiling was going to help them, sort of make decisions about this privacy accuracy trade-off. So once we set this up, this is how the negotiation, the privacy negotiation actually happened. So the owner and the analyst, and then the owner says, all right, at the epsilon we chose, you'll be seeing some kind of expected error in counts and some kind of expected error in quantile estimates. All right, so the analyst comes back and says, well, this is fine. The error in the count is fine, but the error is too great for quantiles. So the first thing they'll say is like, can you just raise the epsilon so we can just get everything with lower error, right? And then the owner says, no, this epsilon is already high enough. This is already a lot of privacy budget expended, so we're not going to go higher than that. But now you can do other things, right? So now you should be able to say, well, at this same privacy budget, if you want lower error on quantiles, well, maybe we can reapportion the privacy budget so that you can have higher error on counts, but a lower error on quantiles, right? And then the analyst comes back and says, hey, that's better. So we care about the error of medians, and so, but we only care about medians. We don't really care about like the 25th percentile and 70th percentile. And maybe we can even drop this gender breakdown. Maybe we don't care about that as well, right? Because if you drop a breakdown, then your group sizes become larger, and so on. So this is how the negotiation happens. And sort of many factors affect the accuracy under differential privacy, right? Like the first of all is overall privacy budget, but even at a fixed overall privacy budget, right, you can sort of reduce the overlap between the statistics. You can reduce the set of statistics you're releasing, right? You can, the sophistication of the differentiated algorithm also sort of impacts what kinds of errors you have. And of course, distributional properties of the data and sizes of the cells, right? And so there are sort of a lot of variables that you can play with to try and accommodate like a request, especially if you know that there are only certain parts of the data that you really care about, right? And you can think of this negotiation also as a way to elicit what do the analysts really care about, right? And therefore sort of try and get accuracy for the things that they care about the most, right? And so these continuing, and in the end, like the owner comes back and says, yes, if we focus only on the medians and drop down to the gender breakdown, the error will come down to 500 and 5,000. And then the analyst says, great, let's do that, right? And that's the sort of end of the negotiation, and now you have a release, right? And the final release is one where the data owner and the data analyst have agreed on the privacy parameters, the workload, and the disclosure review board has completed their final review. And then the final release execution is one where you have like a hardware-based secure random generator, and that doesn't preserve the random seeds. And then the subsequent post-processing may be performed, sort of maybe suppress some higher data items to avoid misuse and things like that, right? So just to sort of recap this whole process, like you have three sort of parties here. So you have the data owner that's trying to impose a global bound on the privacy laws, and which covers all of the releases that they're making and all the statistics they're releasing. The data analyst is now getting access to data that they may not have. And while any sort of analyst request is possible, the strict bound on privacy will limit what kind of statistics will have high accuracy, right? And before, what was happening is like there was a lot of burden put on the data owner to do all of the privacy analysis. That can be pushed down to this sort of privacy software so that it sort of ensures epsilon differential privacy, profiles the error, tries to maximize accuracy for the release for any epsilon, and supports this sort of negotiation. Right? Let's come back to this sort of original figure that I had as a DP researcher, right? This was my worldview of differential privacy research. But if you go to the real world, it's a lot more complex, right? So first of all, your privacy model, do you really only want pure differential privacy? Like nobody tells you I want pure differential privacy, or I want Renyi differential privacy, I want pufferfish, right? They just say, these are my privacy expectations, these are our prior legal requirements, design a solution that works for us under that model, right? And you want to have some reasonable privacy parameters so that it's not like you're giving away the entire database. So there's some flexibility there. The data set is mostly given, but it's also like in some cases it's not fully given, because you need to take into account any sort of what do you call ETL, or like transformation operations or join operations that you need to do even set up that data set, right? The task is often very underdetermined or undefined, because usually the analysts ask, for a lot of queries, right? But they do have some sort of prioritization of the queries that they care about. And so this is where the negotiation comes into the picture. It's often sort of under, they want to do some task and they translate it into a bunch of queries, but those queries may not really be what they care about. The error metric is probably the hardest thing. We usually think that there is a error metric that you want to optimize for, and you need an error metric, because without an error metric, you will try to preserve everything in the data set, right? And this is like the most undefined part of this process. For example, in this previous example, we thought like you're talking about counts and medians, so let's show them like the absolute error, the relative error, and that should be totally fine, right? Absolute average error, absolute 95th percentile error, average relative error, and average 95th percentile of the relative error. But it turns out that's not the error metric they care about. The error metric they care about is after you add noise, if college like Duke University results in higher average salaries than, let's say, Harvard in the true data, then that same property should hold in the noisy data, right? You can't hold with 100% property, but that's the kind of error metric that we would not have thought about. Right? And in terms of the output, you often want to sort of release some way of assessing error in addition to just the output. Like you may want to give some sort of confidence interval or some sort of accuracy profile, and that should happen along with the answer that you're giving. And finally, the privacy parameter epsilon is a negotiation, right? It's a negotiation between the stakeholders and the data owner. So I guess I have 10 minutes now. If I have less time, please let me know. But I think in the last 10 minutes, I will maybe quickly talk about a couple of technical challenges. I won't go too detailed into them, but I'll give you a flavor for what may be some sort of open questions that we need to sort of think about, right? I'll talk about the more technical thing first, like answering multiple queries with differential privacy, and then talk about a little more about the privacy negotiation, which is could be very open-ended, but food for thought for researchers. So answering queries with multiple queries with differential privacy, like this is really what differential privacy is built for, right? Like no other technique can sort of handle multiple queries with the grace that differential privacy can handle. And a lot of research has gone into how do you answer many queries with differential privacy. But the focus of most of this research has been on counting queries, right? Like you would have heard of, and also particularly for linear counting queries, like you might have heard of the matrix mechanism, the HTMM, dual query, the multitude of weights exponential mechanism from the last talk, right? All of these are trying to optimize how do you answer many, many, many linear counting queries on the data set so that you can sort of get the maximum accuracy for a privacy budget. And all of the techniques there try to sort of take your queries that you have and identify like a basis that you can answer efficiently and reconstruct your original queries from that, right? And there are many, many ways in which you can do it, and there are sort of several sort of state-of-the-art algorithms out there, right? Some which we developed in our group. There's also some work on sort of more complex SQL type queries that involve sort of complex joins and self joins. There's been work on graph counting queries and so on. But most of the work has been on counts. So the question is, what about aggregations? Like when we went to this example, they said, no, counts are fine. We also want these medians. And the question is, what is the privacy efficient strategy for answering sets of quantiles, right? Sets of quantile queries. And then we had to sort of actually sort of think and see, and there isn't too much literature out there. So the actual algorithm that we used in our setting was basically we needed like multiple quantiles for the same group of people. And so rather than going with like an exponential mechanism, which probably would give you the best accuracy, we went with a different algorithm, which actually first sort of released a differentially private CDF from which you could just read off the median from as post-processing, or read off the 25th percentile, 100th percentile. And the nice property was like you can release multiple quantiles with no additional privacy loss. But more importantly, like this kind of method was you were able to sort of permit, you could just read off analytical estimates of error, like confidence intervals from the output that you got, right? And that's also an important property, because if it's not easy to get like an estimate of confidence interval, then it's hard to explain how much error there is in an estimate to a downstream analyst, right? And it turned out it gave competitive error even when releasing a single median, not just multiple quantiles. Turns out the same algorithm was used by another sort of data product that US Census Bureau released on a similar kind of problem. So that's okay. If you want to answer sets of quantiles, you can use that. But what about sums, right? We had a paper in TPDP 2019 about how do you answer sets of sum queries. And there the challenge is basically that sums are, as you know, have a higher sensitivity because you may have one outlying value that has a really large value, and you have to be able to cover that, right? Your noise has to cover that. And so you need to have ways in which you can truncate your data set. But a more interesting open question is like, what is the privacy efficient strategy for answering mixed workloads having different kinds of these statistics, counts and medians and sums and maxes and mins and so on? And so I think that's an interesting sort of open question. Another interesting question from when you're thinking about answering multiple queries is like, often in this previous example that I showed you, there was just one stakeholder who wanted a bunch of queries. But often the query requests don't come from a single stakeholder. They come from different stakeholders, right? Like for example, if you're releasing demographic statistics, one stakeholder may be interested only in like small population groups who are of a certain sort of ethnic type, whereas another group may be interested in people based on their median income and so on, right? And now when you have different stakeholders who all have to share the same limited privacy budget, now you have analysts with competing goals, right? And so now you need to sort of think about how they may compete for this sort of limited amount of access to the data or limited amount of privacy budget. And you might like some nice sort of fairness properties to hold there, right? Like for example, the simplest way to answer this would be like to give each of them, their equal share of the privacy budget, and then say, I will just use I will use your share of the privacy budget to run a differential private mechanism and give you answers. But then if two people ask the same question, like why are we unnecessarily wasting, privacy budget independently for them? You could pool their privacy budgets, right? And this is really what all of these state-of-the-art techniques for answering multiple queries do. They sort of try to find these substructures and sort of choose the substructures that they can use to answer the queries. But then when you do that, you want to make sure that certain desiderata are met, right? So for example, you want to have something like sharing incentive, which is jointly answering queries should only release the errors for these analysts. It should not increase the errors. Um, there's an interesting property we came up with called non-interference, that adding a stakeholder with their share of privacy should not increase the errors for others who are already in the system. And then you might think these are sort of obvious sort of desiderata, but it turns out like baseline algorithms and all of this, all the state-of-the-art algorithms violate one or more of these desiderata. And so you actually need new algorithms to satisfy these desiderata and give you the benefits of jointly sort of answering all of these queries. There's a paper that's under review right now, which is also presented at PPDP 2020. But there's sort of a lot of follow-up work that is needed to sort of get to state-of-the-art algorithms that satisfy these kinds of desiderata. The last couple of minutes, I want to talk a little bit about the privacy negotiation again. I think the privacy negotiation is an unavoidable step when deploying any private data release. Because if you are acting as an analyst, you want the moon, right? But if you're acting as the privacy officer, you don't want to give away the moon, right? The fundamental law of reconstruction disallows giving away the moon. And the problem is often underspecified. Like analysts often know what they want, but they can't verbalize it. The perspectives on error utility can vary. Like some terms we get is like, we want quality over quantity. Like we don't, like, here is my request of data, but I don't want all of it. I just want the most, as long as you can give accurate statistics, you want as much of it as you can, or equal distribution of error, right? And data owners want privacy, but epsilon doesn't make sense. Like, how do you contextualize epsilon to something that they can sort of internalize and use? So I think this is a hard problem. And I think some sort of ideas for technical tools that can help the process and potentially spur new research is, I think one important thing is like explaining error introduced by differential private mechanisms privately is important, right? You can't just give the error, right? That can leak information as well. And there's some recent work that's actually trying to do this, but developing mechanisms that permit both the release of the algorithm and the uncertainty estimate is a challenging problem, because a lot of algorithms are not just take the real answer and add noise, right? They come with a lot of pre-processing, or they come with a lot of post-processing, and those steps really cause the uncertainty estimation to become hard and intractable in some cases. Also, making this privacy negotiation itself privacy preserving is an interesting challenge, because if this back and forth happens a few times and each time you're releasing something, you need to make sure that the overall process is privacy preserving, right? And in some cases where we have worked with some organizations, we were able to use simple DP mechanisms that can permit this negotiation without using the data at all, just using analytical estimates of error. And in some cases, that's great. But I think in some cases, like for example, if using a data-dependent mechanism like a median algorithm, then it's hard to sort of analytically estimate what the error is. So you need to run the mechanism to get estimates of error. And so that becomes more challenging as the sophistication of the DP algorithms increase. I mean, this is just sort of, I'm sure all of you know this, like helping data owners contextualize privacy loss parameters is a hard problem, right? I think some people are doing some cool work of creating attack libraries and then showing like, if you have a epsilon differential private algorithm, what kind of attacks does it guard against? And I think, and to what extent, I think that's a good step forward, but I think more research is needed here. And finally, helping data analysts verbalize accuracy requirements is also important, because the analysts usually have some downstream analysis in mind, right? And even sometimes they don't, but even when they do, like they sort of take that and say, what is data set that is sufficient for that, but rather than thinking about what is the data set that is necessary for that. So I think that's an important challenge as well. So with that, I want to end the talk. And to summarize, I think differential privacy is providing a framework for sharing data while managing risk in a quantifiable manner. And more organizations are embracing differential privacy. At least a lot of organizations think it's a buzzword and they want to try it. So it's a good time to try and engage with organization. But getting deployments right is hard. And I think there are some interesting and challenging open research questions in this space. Right? And that's it. Thank you.
Thank you, Ashwin. That was a magnificent talk. I mean, it's you're giving us your view on the real world differential privacy, which seems to be much messier than what we think and what we usually perceive. So we have some questions from the audience, and I'm going to read them first. So the first question, I think you briefly mentioned this point in your penultimate slide, but the question is, how do we make sure that negotiation per se does not cost any privacy loss, or any idea of how to measure the privacy loss of in the negotiation stage?
Yeah, that's a very good question. I think there are many answers here. I think one, I sort of briefly alluded to one idea, which is, if you can make this negotiation happen without access to data, that's great. And in some cases, we have successfully did that, and it worked great. Um, I think another way to think about it is like, who are you releasing the data to, right? Like in the previous example, like, I mean, even though there are two levels of release happening. One release happening to, fairly trusted government agents, federal statisticians in like the Department of Schools, who in turn are then going to release something to the public, right? And so when you think about privacy loss there, you may be able to do some fine-grained accounting as to like, is the privacy loss happening only to the people at the Department of Schools, or is it happening out to the public as well, right? But I think in general, it would be great to have a mechanism that can sort of bound privacy laws across the entire negotiation. And I think sort of ideas from differential privacy already sort of exist. Like one of the motivations for the sparse theory technique, for example, was to be able to do something like this, like a cohort estimation problem. And so there exists ways to solve this, but it'll be interesting to see, like, the solution will depend on which kind of use case you're solving.
Right. Yeah, and also I guess that implies also the number of questions that you can actually answer during the negotiation process, which might create a further level of difficulty in this process.
Right.
So the other question, the second question that we have here is from Christine, and it's so when we're talking about accuracy versus accuracy disparity trade-off, that makes clear sense in the context of allotting different amount of privacy budgets across overlapping queries. But often bias fairness concerns are focused on disparity across different population groups. So, and there is a parallel between the sequential composition on the former case and the parallel composition on the latter case here. So in your college stats deployment, did you identify and evaluate for any accuracy or accuracy disparity trade-off across different population groups, either split by demographics or split by geography and college type?
Yeah, I mean, I think from our experience, a lot of the accuracy disparities um, arise in one of two ways. So one way is basically you're adding noise that is somehow more for one subpopulation and less for another subpopulation, right? Or you're adding noise uniformly across everyone, and then you're doing some weird post-processing step, which is sort of screwing everything up, right? In the college scorecard case, it was a simpler setting, and in fact, like one thing we tried to do was not like we were adding noise sort of roughly the same across everyone, but I think one thing we tried to do is not to do post processing, but rather use something like suppression. And so the kind of disparity you might see is like small groups will not have data published, whereas larger groups will have data published, and that's something that's I think there is some disparity there, but it's also much easier to explain to the user why some small groups data was hidden away. But beyond that, we did not do any sort of fine tuning for accuracy disparity.
And if I can add here one further point to this question, are the user to which you work to interested in this type of aspects here?
Yeah, I mean, a lot of users are interested in ensuring fairness or ensuring that there is no sort of lot of disparity between in the accuracy, because I think that's one sort of fundamental thing about when you're releasing data for social good, you want to enable things like research and policy making, right? So their downstream users care about these things, right? Like you don't want to sort of disadvantage certain population groups, saying that, hey, your median salary is going to be low even though their median salary could be high, right?
Right.
And so I think that's an important, it is an important characteristic.
And you do though make this type of analysis post ante. So this type of auditing, I guess, will bring another level of complexity
Correct.
to the table, because it may leak further, um, further information, especially if you have to query some of the attributes of the users that might be useful for analyzing the fairness impacts that you might
That's
not
possible.
have
Yeah.
taken into
Mhm.
account, like. So you, for instance, you were mentioning, well, let's get rid of the gender, but actually that might be an information that you might want to
Right.
need to audit fairness, and so that's
Right.
for this level of complexity.
Right. I mean, there was a recent executive order that says you people have to disaggregate to a certain extent to ensure equity, right?
Right.
Signed in the new administration in the U.S. So yes, that use case is there.